up to you today. Okay, and the audio? Is the audio on?
Yeah.
Okay, perfect. There's my clicker. All right. So this class is probably going to end a little early. I was originally going to talk about CTCs and sequence-to-sequence modeling in today's class, but then as I realized that once I began making the slides, that if I want to combine everything that I wanted to cover, the whole thing is going to take an awful lot more time than just one class. So I've decided to kind of split it, just set up some preliminaries in this class, and then actually talk about the CTC problem and the attention-based models in the next class. This means that the schedule is going to slide a little bit. To make up for it, we were supposed to be having 2 lectures on variational autoencoders. I'll probably try to shrink it to 1. And we're going to have to pardon us for rushing through that topic. The second aspect of it is that when I cover all of these, it's not 2 full lectures. It's actually 1 and maybe 3/4 or 1 1/2, right? So I'm going to today. I'm probably going to stop 5, 10, or 15 minutes early, unless I've completely misjudged the amount of time this is going to take. And the next class is also going to be short, so come prepared with any questions you might have to fill in the rest of the time. Just assuming that I don't actually consume the entire class. Okay. So the task, what we are going to be talking about today is, and in the next class is how we set up the loss functions that we optimize for recurrent neural networks. And in the next class, we're also going to look at how we can modify standard recurrent structures for complicated tasks. So a quick recap. We've seen in the previous class that recurrent networks can be incredibly effective. Here we saw this example where a recurrent network, this was actually one of Andrei Karpathy's bigger networks with many, I think millions of parameters, but it really learned to generate code. If you've seen his page, you can actually download his the code that he used to train the networks and generate these data. And if you're actually, Ryan's not here, but we also went through this issue of how you could train recurrent networks to generate text during the recitations, right? So now what we've seen is that you can have iterated structures for analyzing time series. Recurrent networks are a mechanism for analyzing time series data. And the simplest mechanism for analyzing time series is to say, any output is dependent on the current and past inputs. And this was a simple iterated structure, which was also our time delay neural network. But a better structure for analyzing time recurrent series time series data are recurrent structures, which allow you to look into arbitrary amounts of time in the past. Now, we also saw that these structures can be variously designed depending on what kinds of modes you want and so on. But they have the ability to carry over information over effectively infinite amounts of time, which is basically what we want when we're analyzing time series. A third point we noted was that recurrent structures, although are originally proposed as a mechanism for analyzing time series data, are also useful in other situations where you might potentially, which look more suited for, say, multi-layer perceptrons. So, for example, if you are just trying to train a multi-layer perceptron to add 2 binary numbers, the number of training examples you would have to provide to this network, even if it had appropriate architecture, is going to be exponentially large. You're going to have to teach it about how to respond to every possible combination of inputs. And even after providing loads and loads of training instances and their corresponding outputs, you really have no guarantee that it's going to learn to do exactly what you wanted to do. And even if you manage to do all of that, A, the network is going to be very complicated, and B, when you train a network to add 2 n-bit numbers, if you can't provide it an n plus 1 bit number. On the other hand, if you were doing it with a recurrent network, this is going to be, you'd need a recurrent network with maybe 4 neurons or 5 neurons, something really small. And you could just train it on a small number of examples, and it would learn to generalize, because the basic operations are really very few when it comes to performing addition. And you'd effectively end up performing what an MLP was supposed to perform using far fewer parameters. And you'd be able to learn this robustly from far lesser data, right? So recurrent networks are not just great at analyzing time series, they are also very versatile in other sorts of forms of ways, in that you can actually use them in tasks with iterated computation, like in addition or computing parity and several other tasks like that. So we saw that recurrent structures can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. So for example, if you were using the recurrent network here to learn how to add numbers, what you would really be providing is sequences of inputs, and then you'd get an entire sequence of output bits, and you would compare that to the desired sequence of output bits, and that's what you're going to be using to update your update your recurrent network. So you wouldn't be updating it 1 bit at a time, you'd be looking at the entire output to make sure that you got everything right. So in general, you're going to be minimizing a divergence between what the network outputs over the entire series and the output that you desire over the entire series. So you'd be looking at the entire sequence of actual and desired outputs. You can actually perform the training through gradient descent and back propagation once you define your divergence in this manner. So the primary topic for today and for the next class is how exactly do you define this divergence. I will not really be going into too many examples for the day, but hopefully I can look at some more complex examples on Monday, I will say. But the point is that these divergences can actually, how you define these divergences can actually make life very difficult. We also saw that the standard recurrent network as we originally defined it has issues with stability and memory, right? Although the intention was for it to carry over information over extended periods of time, if you used, say, sigmoids or ReLUs and the hidden activations, sigmoids would just saturate very quickly and there's no more information being carried. There's no additional stuff you can give it, so it's not really performing the task of remembering things. ReLUs are going to blow up. So which means that once they blow up, they really are not carrying anything useful because they become highly sensitive to even small changes in the input. And we found that we need some kind of activations in between. So we found that that's empirically observed, but you can also work this out with math, that tanh activations have this nice characteristic behavior where although they do tend to saturate after a while, they carry memory for longer periods of time. Which is why when you actually use recurrent networks, you will find that in the hidden layers in particular, which are the recurrent layers, the actual activations that you will use are tanh and not sigmoids and ReLUs, right? Or other kinds of, or you will use bipolar activations in general, things which have both positive and negative components, so that they have the ability to carry information for longer periods of time. Now, we also saw that when you're actually performing the training with using gradient descent, if you give it some input and you get the output after a long period of time, you have to carry information about what happened to the output back through time to the very beginning to see how small changes in any parameter could affect the output. And to do that, you need to compute the gradients. And we found that in general, when you have networks with many, many layers, and a recurrent network we saw was really just one really deep network, effectively of arbitrary depth, where the depth depended on the length of the input. It was a feed-forward network, where information flowed continuously from the beginning to the end. So in general, when you have feed-forward networks of this kind, as the depth of the network increases, we can even see through the math that the gradients sort of tend to become fainter and fainter as you go back. What really happens is that most parameters end up not affecting the output very much, and a small number of these will affect them a great deal. So most gradients are going to vanish, some of them are going to explode. And if you actually plot the gradients as a function of layer going from someone's got an alarm to wake up. Okay. So if you actually plot the gradients going from the output layer to the input layer, you can see in the picture that as you go up, the gradients become basically kind of vanish. So we had all of these issues. And we found that the basic recurrent neural network structure that we saw has problems with memory. Things fade. And the reason things fade is not because of the input. The fading behavior is a function of the network. Meaning, depending on the weights matrices, depending on the activations that you use, any trigger that you give it is going to be remembered for only so much time, after which it's going to either die out or its effect is going to saturate out. Whereas what we really want is something where the memory, the ability to remember something really depends, or when you choose to forget something must depend not on the structure of the network, the parameters of the network, but on what you have seen. So we saw as an example that if you were trying to parse a program, if you saw the opening of a loop, you had to hang on to the knowledge that a loop has been opened until it was effectively closed, knowing that anything could happen in between. And so there's no fixed memory that you should have. There is an input-based trigger which says, okay, I have seen the end of this loop. Let's forget that this loop was opened. That means we needed the memory to be the long-term dependencies not to be dependent, dependent on the network parameters. We want long-term memory behavior to be triggered in response to the input. And so we saw that there was a standard variation of recurrent neural networks, which are these long short-term memory neurons, which explicitly got rid of nonlinearities and weights, because these were what actually introduced this fear of fading or exploding or saturating, and instead went back and looked at the inputs to switch off or switch on the memory, thereby addressing the primary problem that we just saw. So all of these were what we saw in the last class, right? Now, LSTM-based architectures we saw were identical to standard recurrent architectures. The only thing that happened was each of these boxes, which really, as we saw, is a vector of neurons going into the page, is now an LSTM unit. It's not just a simple perceptron. And we also saw that these things could have bidirectional, all of these networks could have bidirectional variants, where you might be considering, you might be processing data left to right and right to left at the same time, and the final decisions you take are based on the inferences derived from processing the data both ways, right? Onwards. So the key issue over here is how exactly do you define this divergence? Our ability to train the network depends on defining the divergence. How do we quantify the error between what the network outputs and what we actually want from the network? So first, to understand why this is important and how this actually influences our training, let's go back and look at what happened when we try to train the network. We are going to perform back propagation through time. Why do we call it back propagation through time? Because you have a time series, and the error is being propagated backwards through time from the end to the beginning. That's how the gradient descent was, the back propagation was performed to compute and aggregate the gradients that we would plug into the gradient descent algorithm, right? So you'd be given a collection of sequence inputs where X is going to be a sequence, each with its desired output D. Well, my notation is slightly inconsistent today. I'm calling it D over here. In other places, I call it Y target, but hopefully it shouldn't be, it shouldn't confuse. So each training instance is going to consist of a sequence of inputs X, which could be anything. In the homeworks that we saw, we had these training inputs as sequences of log spectral vectors, right? Or maybe images. And the output is a sequence of desired target values. Now, here I've represented X as a sequence T long, which is a T long input sequence, and the desired output D as also a sequence T long. It needn't necessarily, the two lengths need not necessarily be the same, right? So for the way we did it, for each training input, we had a forward pass. We would pass the input through the network. It's going to produce a sequence of outputs, and then you'd have a backward pass where you'd actually have a divergence defined at the top, and you're going to compute the divergence of the derivative of the divergence with respect to the parameters of the network, and that backward pass computes gradients backwards from the end to the beginning through back propagation. That's why it was BPTT. Now, specifically, we noted that when you think of the divergence is defined between the sequence of outputs of the network and the sequence of desired outputs. So this means this divergence is not necessarily just the sum of the divergences at individual instance. It could actually be any odd thing. What we are really trying to compute is, do we have the, maybe I can write here. Can they see this? Probably not. Okay. So we don't have the other camera, right? Oh, fine. So this pen has, I'm looking for the properly black pen. Well, the blue should do, hopefully. So what we're really looking for is the divergence between y1 of, y of 1 through y of t, and say y target of 1 through y target of t. Now let's just hold this thought in mind. This is what we really want. Now this doesn't necessarily mean that this can be written as a summation over t of the divergences between y of t and y target of t. So this is not necessarily implied, right? But we will make the assumption in many cases that this is exactly what the divergence is going to look like, but keep in mind that this is not necessarily implied, and we will look at some examples of where this is not really going to hold true. Anyway, so the first thing is, once you define the divergence, the first term we want to compute is, although the divergence is defined doesn't break down in this manner, although it does not break down in this manner, right? This doesn't hold. The divergence itself is a function of the individual outputs, and so you can compute a derivative of the divergence with respect to each of the individual outputs. And once we compute the derivative of the divergence with respect to each of the individual outputs, the rest of back propagation is just exactly as we've always had it. There's nothing novel about it once we get to the derivative of the divergence with respect to the outputs. So the key problem over here is to be able to compute this divergence, because once we compute it, which is the divergence with respect to the outputs of the output layer, then you can compute the derivative of the divergence with respect to the input to the output layer and pass that on, and the rest of backpropagation follows, right? So the key component of all of this is the computation of this derivative, and this depends on the definition of the divergence, which depends in turn on the network structure itself. So here are the various variants of the network structure that we've seen in class earlier. This is just a conventional multi-layer perceptron. In a conventional MLP, a single input goes in, it gets processed, a single output comes out. Now, or we could have sequence generation, where I give it a single input, and it sort of processes the input and produces a sequence of outputs. Or you could have a sequence of inputs going in and a single output coming out. Or other combinations where a sequence goes in and a delayed sequence comes out, or the one at the end, which we can think of as a superset of everything else that we've seen, where you have a sequence of inputs going in and a sequence of outputs coming out, right? So let's consider this first thing over here. This is something that we are all very familiar with. We've seen this from the very first class, right? So here, this is what the actual, suppose I were using a simple multi-layer perceptron to compute, to process my time series. Then at each layer, at each input, I'm going to be applying that MLP and generating an output. That MLP transfers no information into the future. So the same MLP is going to be working on the next input and producing the next output. And then it's going to work on the next input and produce the next output, right? But now, if I want to train this network, I can still think of this as output as a time series, right? And now I can still compute a divergence between the sequence of outputs and the sequence of desired outputs. Now, this doesn't necessarily mean that I'm going to have one-to-one, that the divergence breaks down as divergences at individual instance. For example, if I were to write the divergence as something like this, which is just a generic function. If I write this as t some function g of y of t, comma y target of 1 through y target of t. So this is just that each time my input is somehow being combined with the entire sequence to give you a value which quantifies some kind of error. And suppose I added this over all time, right? Now, the error, the loss that I'm looking at is now a sequence loss, although the network itself is operating on one input at a time, right? So, which just goes to tell you that you don't necessarily need recurrent structures in order to be able to consider sequence losses, although we won't specifically be looking at this this particular form, most generic form of the divergence for now. Okay. So now suppose we make a very common assumption in all of these, and the very common assumption that we make is that this divergence over here really depends only on t. In the situation that we just saw. Again, keep in mind that this is not necessary, right? So I should probably come up with some reasonable examples which will explain why this is not necessary. But then if I make this assumption, the divergence between the sequence of outputs and the sequence of inputs sort of breaks down into the sum of divergences at each time. I can think of it even as a weighted sum of divergences, right? So for example, I might say that an error later in the sequence is more important than an error early in the sequence. Most commonly, we'll just assume that all the weights are identical, right? And so if I want to compute the divergence, the derivative of the divergence with respect to any given input, the output at any given time, that's simply going to be the weight at that corresponding time times the derivative of the local divergence, because I've defined the global divergence as a sum of local divergences. Keep in mind that this definition is not necessary. I could have other definitions. This tends to be the most common assumption. This is what we will work with, right? So the most typical example that we've seen for MLPs was at each instant, we would just compute the cross entropy, right? So for example, in your first homework, you were classifying individual frames, remember? And when we were classifying individual frames, you were classifying each frame as computing a divergence for each frame, and the global divergence was just the sum of all the divergences of the individual frames. At each frame, you were looking at a cross entropy between the target output at the frame and the actual output, and you were summing the whole lot, right? So typical divergence for classification tends to be a cross entropy, like we had in the homework. But if you're trying to make a continuous valued prediction, if you're predicting performing some regression, this could be an L2 loss. Regardless, we're sort of decomposing the divergence down. Now, but let's then go to the next slightly more complex problem, one-to-many, right? So here, you have a single input, and you're producing a sequence of outputs where the outputs are recurrently dependent. So the output at each time depends on what happened at the previous instant. And the hidden units could be recurrent units, standard perceptrons, LSTM units. It doesn't really matter. So a single input produces an entire sequence of outputs of arbitrary length until it's terminated by some criterion, like an upper limit on the length, or if it produces some symbol which says you must stop producing additional output. So our typical example is predicting the state trajectory of a system in response to an input, right? I'm triggering the system. How is it going to evolve through time? So here, if I wanted to learn this, now the forward computation is straightforward. I give it the input, I just produce the outputs. But if I'm trying to learn the parameters of the network, then again, I'm going to have examples where I have the trigger input and the sequence of outputs that I would like to see in response to this trigger input. And the sequence of outputs is going to have some length. So I'm going to assume that the actual recurrent network itself produces outputs for that length. And now I can just compute my gradient as the divergence. I can compute my loss as the divergence between the target output sequence and the actual sequence that I've generated, and compute my gradients as before. And once again, a very common assumption that we will make is that you have a one-to-one correspondence between the desired and actual outputs. So if you have T outputs in the target in the target output, then it's common to assume that the network is also going to produce T symbols, right? Now, you can think of a situation where it produces T symbols, but then you have intermediate steps of computation where there is no output happening, which is perfectly acceptable. But the standard assumption is that you have a one-to-one correspondence across time. And then in that case, the divergence computation just breaks down just as it did for the MLP. The most generic situation is something like this, where I have a sequence of inputs and I have a sequence of outputs. So here you have a simple recurrent computation of outputs. A sequence of inputs produces a sequence of outputs, and now you have exactly as many outputs as inputs. So the output computation is utilizing recurrence, like things like simple examples where I'm not performing classification, is I could be looking at all of the stock values for the past infinite time, and I'm predicting tomorrow's stock value. So at each time I'm doing a continuous valued prediction, right? Or I could be looking at a sequence of words and predicting the next word in the sequence. Various things. So you can think of where you can actually have, these are just trivial examples, any number of examples of this kind. Now, the actual computation, again, going left to right is straightforward. You just have the sequence of inputs coming in, you can produce a sequence of outputs. The issue now happens with training. So you would be given a collection of training examples where X is now a sequence of inputs, t long, and the target output is also a sequence of outputs t long, right? And we must compute a gradient between the t long sequence of outputs and the t long sequence of target outputs. And then we can compute the derivative of that gradient. I mean, we must compute the divergence between the two. And then you can compute the derivative of the divergence with respect to each of the outputs and propagate them on backwards. So the usual assumption over here again is that there's a one-to-one correspondence between the desired and target outputs. And an assumption once again is that, a common assumption is that you can actually decompose the divergence into a sum of many local divergences. And once you decompose it like so, then you can actually compute the derivative at any time as simply the derivative of the local divergence at that time with respect to the output. Again, this is an assumption. This is not necessarily true, right? You can always think of divergence functions which don't have this behavior. But this makes computations very convenient, and most problems that we work with, this actually works. So here's an example. I'm going to step aside from the main theme of the lecture today and talk for a few minutes about modeling text. So we'll come back to the business of learning neural networks, recurrent neural networks. So let's say I'm trying to learn a model that can predict the next character given a sequence of characters. Or at a higher level, I give it a sequence of words, 4 and what years, what is the next word, right? And you're going to say ago, it's just obvious. So how do I look at a sequence of words and produce the next word? Given a sequence of words, predicting the next word. Or if I give you something like yesterda, and then what's the next character? You're going to say y, yesterday, right? So given a sequence of symbols, you want to predict the next obvious symbol in the sequence. When the symbol could be a character or a word. Now, in this case, first, some basic preliminaries. When we are speaking of predicting text, the inputs are discrete. So when the inputs are discrete, the inputs are really symbol sequences. And the network can't really take symbol sequences as inputs. So the network needs real valued vectors. The first thing we're going to do is convert our symbols to real valued vectors in much the same way that we actually converted our output classes to real valued vectors. We're going to make it one hot. Now the first thing you will need to do is that you're going to have to specify the symbol set for the input. You cannot work off an unspecified symbol set. So if I say that the inputs are characters, then there are, in English, there are approximately 100 possible characters. The 26 lowercase characters, the 26 uppercase characters, the digits 0 through 9, various funky symbols that you'll find on your keyboard, semicolons, colons, parentheses, etc. So 100 characters will roughly span the lot, right? So you're going to have to specify the set. If you are trying to predict words, then you're going to say, here is the collection of words that I'm going to be working with. I cannot process any word that's not in the set. So yeah, you're going to be specifying your vocabulary. And now the input is going to be presented as a sequence of one hot vectors. So if my symbol set has v possible elements in it, each symbol becomes a v-dimensional vector where all components but one are 0, and one of them is 1, and the specific component that is 1 is at the index corresponding to the symbol that represented by that index, right? If I arranged all of my alphabets or all of my words, for example, if I'm working on words, if I arrange them alphabetically, the very first entry is going to be just the word A. So A is going to be represented by 1 followed by several zeros. The second word might be, say, Aaron. So Aaron's going to be represented by 0, then there's a 1, and then followed by many zeros, and so on. Standard one hot representation, right? Now the problem with this is that, so the dimensionality is going to be very large, because if I were working off English characters, I have a simple character becomes a 100-dimensional vector. If I'm working off language, and I'm working off a vocabulary of 100,000 words, each word becomes a 100,000 dimensional vector, right? Which is kind of absurdly high. the output over here, when I'm trying to, so going back here, if I'm trying to predict, look at a sequence of symbols and predict the next symbol, what I'm really going to be predicting is a probability distribution of all the symbols, right? So once again, the way it's going to be, if my vocabulary, my symbol set has V entries in it, it's going to be a distribution over a V component distribution. In this case, I think he's actually showing log probabilities. So the output is the probability distribution of our symbols. At each time t, the output I is going to be it's going to be the ith component of the output is going to be the probability of the ith entry in the vocabulary given all inputs or possibly all inputs until that time, right? So this should have stopped at t minus 1. So at each time t, you're going to be at each time t minus 1, you're going to be looking at all words until t minus 1 and predicting the tth word. So the output is a probability vector where the ith entry shows the probability that your guess for the tth word is the ith entry in the vocabulary, right? Now I can define a divergence standard. So I have the divergence between the target sequence of words or symbols and the actual sequence of symbols that I've generated, which is simply going to be, now each of these, at each time, the actual output is a probability distribution, right? And the probability distribution assigns a probability to the correct word. And if you simply work out the cross entropy, you've seen this before, at each time, the contribution of the cross entropy at that time is simply going to be minus of the log of the probability assigned to the correct word by the network. So if you minimize this loss, you're maximizing the probability of the correct word at the cost of the other words. And eventually you're going to be predicting if you got this just right, you're going to be predicting only the correct word at each time, right? Now, if you're modeling language using neural networks, the idea here is what we're really speaking of when you're speaking of something like this is a model that represents symbol sequences. And if these symbol sequences are characters or words, you're really modeling language. So let me continue the segue into modeling language. Remember, what we did over here when we were looking at which open source project, we were generating symbol sequences, character sequences. And the sequence of characters that we generated actually ended up looking like a program, right? So what was the network, what was the underlying model actually capturing? It was capturing the structure of language. This was a model for language. So if I were modeling, the standard problem in modeling language is you're given a sequence of words or characters and you're supposed to predict the next one. So if I said 4 score and 7 years, what's the next word? It's going to be a go, right? If I said the first few characters are A, B, R, A, H, A, M, L, I, N, C, or L, what's the next character? It's going to be an N. So given a sequence of symbols, you're predicting the next one. This is the primary task. And the way we'll do it, as I just mentioned, is to represent the words as one-hot vectors, specify a vocabulary in sorted order, represent each word by an n-dimensional vector with n minus 1 zeros and a single one in the appropriate position. We could do the same thing with characters. So if you're working with characters, this one-hot vector is going to be 100-dimensional, right? So a very simple way of thinking about predicting the next word is to say, wait, this should have been, I'm not really sure what this w_1 is, but you can think of a function f which operates on the sequence of the first n minus 1 words and produces the nth word, right? So the generic representation for something of this kind is going to be some function f which operates on the entire sequence of words from 1 to n and produces the nth word. Now the standard thing that we will do is, which are basically one-hot representations, right? But then here you have a dimensionality problem. All inputs are very high dimensional, but they're also very sparse. What do I mean by sparse? Consider that I have a vocabulary of 100,000 words, right? So these 100,000 words are being represented in a 100,000 dimensional space. But in this 100,000 dimensional space, I have only 100,000 points. As I increase the dimensionality of the space, and the volume of any object increases exponentially, right? Dimensionality of the space, but the number of points I'm putting into it is linear. So if I added one more term to the vocabulary, the space encompassed by a hypersphere is going to grow by a power. The number of points in it is going to increase by 1. So the one-hot representation basically only uses some corners of the unit hypercube. It's going to use an n-dimensional space, but it's going to use only n corners of the two n-dimensional hypercube, and each input is just a point. So the total volume consumed by all of your possible inputs is 0. You have this high dimensional space, and the actual volume that you're consuming from the space is identically equal to 0. Moreover, if you think of it in terms of density per unit volume, density of points per unit volume, it's going to be the order of n over r raised to n, where r is the radius of any unit sphere that you might choose. That holds the entire data, right? So this is essentially a tremendously inefficient use of dimensions, number one. And secondly, by just having this high dimensional representation, you're forcing yourself into working in high dimensional spaces where you know that most of the space, in fact, the entire space is empty. You're never really going to be visiting any of the space. What I mean by this is that these are just discrete points, right? So 0, 0, 1 has a meaning, but 0, 0, 1 plus epsilon has no meaning. So this, although we are thinking of this as something real valued space, our data are not real valued. They're very discrete valued, and you can't even jitter off of it by a tiny amount and get to anything meaningful. It has no meaning at all. So we try to sort of compact this thing down to something more compact. Now, why did we actually use a one-hot dimension in the first place, a representation in the first place? Yes?
If it is one-hot, it means there is only one, rest are 0.
Rest are 0.
So if I determine one position, the rest will be right.
So this is for representing the inputs, right? If I have a word, then how do I represent each word?
It seems like the space is unpassable, different positions, one, right? The input space.
The input space, if I have a vocabulary of n words, you're just having n. You just use n locations,
Yeah.
right?
So the space is not very huge. It's not exponential.
It's an n-dimensional, right? So think of this. If I have a vocabulary of 3 words, so if I have a vocabulary of 3 words, the only 3 vectors I'm using are these 3. But if I draw a sphere of radius 1, what is the volume of the sphere, right? If I go up to dimensions, if I draw a sphere of radius r, right?
Combining different characters together.
You're not even speaking of combining different characters together. I'm just saying that, think of it this way. If I have only 2 words in my vocabulary, you live in a 2-dimensional space, right? I can draw a circle. How many points are there in the per unit area within the circle? It's going to be 2 divided by r squared, correct? Now if I add a 3rd dimension to it, if I add a 3rd word to my vocabulary, now I'm in 3-dimensional space. The radius of the volume of the sphere is going to be r cubed, but it has only 3 points in it. So the density is n over 3 over r cubed, right? If I go up to 4, it's 4 over r raised to 4. Basically, you're not using the space. It makes sense to you? Right? So the space the capacity of the space keeps increasing exponentially, but the number of points you're using in it is going up linearly. So it's a highly inefficient use of your space. The reason we actually use one-hot representations is very simple. You don't want to say that 2 words are closer than the other two. So when I have a one-hot representation, the distance between any two words is exactly the same, which is why we want to use one-hot representations. But this comes at the cost of, blowing up the capacity. So why don't we project the points down into a lower dimensional subspace, which is what we'd ideally like to do. The reason we didn't do it was that we didn't know what the actual arrangement of points in the lower dimensional subspace must be, because we have no idea about what must be closer and what must be further. But if we learn this projection into a lower dimensional subspace from the data itself, presumably the notion of what is closer and what is farther will be learned automatically in the learning process. This is really what we're going to do. And the thing about going down, say, from an n-dimensional space to projecting it down to an m-dimensional subspace, hyperplane, is that the density is now going to go up, because if I look at if I take a radius r and create a volume around all of my points, instead of density is going to be being n over r raised to n, it's going to be n over r raised to m. So you're making it, once again, you're making a more efficient use of your space. You're going to also need fewer parameters, right? So, and if properly learned, the projections of all of my points on the space will be such that the distances between the points actually tell you something about the relationship between the words. So the standard technique over here is that we're going to start off with this one hot vector representation, and then we're going to project it down through a matrix P to a lower dimensional space. So lower dimensional representation. So every Wi is now a one-hot vector, but I'm going to multiply it by a matrix P, which is m cross n, where the one-hot representation is n-dimensional. So m cross n is now going to live only in m dimensions. So if m is less than n, I'm actually reducing the dimensionality of my representation. And each word now is represented by p times w, right? So the ith word, which was represented by the one-hot vector wi, is now represented by p times wi. And if p is properly learned, then you expect that the representation in this lower dimensional space actually has some meaning in terms of the arrangement of data of words on this lower dimensional space actually has some meaning. Now, if P is a matrix, I can represent the matrix P as a single one-layer neural network with linear activations, right? Exactly what a matrix operation is. And if the same P is being applied to every word, then all of these networks are identical. So when I'm trying to make a prediction of the nth word based on the first n-1 words, it's like saying I have this network with n-1 copies of the same projection network being applied to the input. And the output of these networks is going to the subsequent network, which might be anything which might be making its predictions, which is finally going to predict the next word. And I can just train this using back propagation, right? So if I were assuming that I'm actually going to be applying this projection to reduce the dimensionality of the vectors first, then if I were using a time delay neural network model, where every word is going to be looking at, I'm going to predict any word based on the previous n words. This is the iterated structure. This is not a recurrent structure, right? So every word is first going to be projected down using the matrix P. Then the projected down word components are going to go into your predictor, which is a network, which is going to predict the next word. So at each time, at W4, you'll be predicting W5. At W5, you'll be looking at how many are, W2 through W5, and you'll be predicting W6. At time 6, you'll be looking at W3 through W3, 6, and predicting word 7, because you're always trying to predict the next word, right? And of course, if I have training data, I have all of these words, I can compute my errors and I can train my projections. So one of the outcomes of this learning this model is that first, I learn to predict the next word, but I also learned a lower dimensional representation of the data itself. Yes?
The lower dimensional representation, is it always choose m, if you have n dimensions, is m one less than n? Is it?
You want to, it's lower dimensional, so m has to be less than m,
Yeah.
right? And so typically, so eventually it ends up being empirical, right? But it turns out, at least in the case of characters, in some of the examples that we've run, you can go down to 5. It just makes, from 26, from 100, works just fine. So now there are alternative projections, ways to actually doing just this, right? Now, if the objective is to learn the projection of words into lower dimensional spaces, you have other models. This is something called the soft bag of words model, which is going to be which predicts any word based on a certain number of words from the past and a certain number of words from the future. And you just do a mean pooling on. You make projections from all of these words, have a mean pooling, and predict the next word. Or you have something called the skipgrams, which predicts all of the adjacent words based on the current word, right? All of these are different variants of making predictions of language, predictions of words in a sequence based on other words in a sequence. And in each case, the models can be learned using just straight up backpropagation. The key component is that you're trying to learn the projection into that we will call an embedding of the word. And there's a recitation that we will be having later about how to actually learn these embeddings. But then the reason I'm actually talking about embeddings is that they have this very nice characteristic. It's nothing specific to language. Anytime you're working with a discrete set, the problem with discrete sets is that you have no way of assigning importance. You can't say symbol A is closer to symbol B, but you can actually learn the relative arrangement of these symbols in a topological arrangement of these symbols through an appropriate prediction task, right? And in the case of language, if you actually do this, here's an example from Thomas Mikolov's paper in 2013, where I think this was based on skipgrams, and they find this very interesting relationship. They report many such relationships, right? The vector that connects China to Beijing ends up being the same as the vector that connects Russia to Moscow, or Japan to Tokyo, or Poland to Warsaw, and so on. So the actual positions, the relative arrangements of these words seem to capture semantic meanings, right? We'll have a lot more on this and the recitation. But then let's go back and look at how we actually trained, how we can use this for modeling language. So we would have the sequence. If I were to train a network of this kind to model language, what we looked at earlier was to predict each word based on a fixed window of words from the past. Ideally, what we want to do is to look at the entire history of words going all the way into the past, right? And for that, we need a recurrent structure, which would imply a model of this kind, where you have one or more hidden layers of maybe LSTMs, right? And we're going to be looking at all the words until some point to try to predict the next word. Now, you could actually train this network from sequences of words where at each point the target output is the next word. And you can use backpropagation to train this network. So you could use this now to generate text, which is basically what we saw in Karpathy's examples. I could provide the first, say, 3 words in the sequence, right? And at each time, it's going to produce a probability distribution over words from which I could draw the next word, feed it in. It's going to produce a probability distribution over the words again, from which I can draw the next word, feed it in. Again, word or character, depending on what you're modeling. And that's exactly how this particular bit of text was generated. He trained a large network on a very large network on Linux source code, and he just ran it. It actually produced, and we saw the mathematics, the thing that looked like a theorem. He actually trained a network on LaTeX code, and it ended up producing LaTeX, which actually compiled after a little bit of fixing into theorems and figures, which is pretty impressive, right? So these things tend to be remarkably effective. And this one is one of my favorites. So these guys are actually training a network on music. If I can just, maybe I can play this. Just bear with me. It's easier to play these things on. some reason. Yep. Can you hear this? Where's it coming from? So this was just this was just trained on and I was made to generate more piano music. It sounds totally authentic to me. It looks like it could. I don't know, but I don't know if it will be an operating system. Right? Anyway, we're sort of segueing off onto the side about how we can actually model text and make predictions and so on. But let's get back to our primary problem, which are defining divergences in general. So let's go to first start off with a very simple problem, right? Where I have a sequence of inputs and I have to produce one output. So can you think of an example? Your homework 2. I have a sequence of log spectral vectors. We asked you to predict the phoneme after you saw the entire sequence, correct? So simple example, I could be giving you lots of segments of speech, and when you've seen it all, at the end of it all, you have to predict your phoneme. This is an easy example, right? So forward pass, it's easy. I have a fixed length of input. I just produce the output, pass it through. Eventually, at the final input, I'm going to get a probability distribution over the symbols that I'm choosing from. I can pick the best one for classification, right? But then keep in mind that there's nothing sacrosanct about the last input. I could be producing outputs at every single input. It's just that we don't, because we don't care. We are going to make the classification only after we've seen the entire input sequence. But what if I didn't give you the entire, suppose instead of giving you, in the first experiment, I gave you a 15 vector sequence and said this represents a phoneme, right? Then instead of giving you 15, I just gave you the first 14. Are you going to be unable to classify it? No. You're just going to perform the classification after having seen 14 of these, right? If I gave you 13, you could perform your classification after having seen 13. So in principle, you're actually producing an output after each input. You're just discarding the first n minus 1 and retaining only the last one to make your final prediction, right? So now, this is what we've got. We've got the entire sequence of inputs, and at the final time, we're going to produce a single output. If I'm training my network, the output is going to be one of many classes. If you're doing phoneme classification, I give you the ground truth symbol. And so at the final input, I can compute a divergence between the target output and the actual output. I can propagate the gradients with respect to the divergence back through the network and learn all of my parameters, right? Great. But is this really an efficient use of my data? Not really. And why is it not an efficient use of my data? I'm ignoring what could have happened over here. And I know that that through the input, the output symbol did not change, right? Really, in principle, we are pretending there's no useful information coming out of these, but there is. We know those should have also been the same symbol. So we could, instead of this, so what we could be doing instead is to be assigning the same label at each point. And when we do so, what have we done? We've taken this many-to-one mapping and converted it back into something that we are already familiar with, which is a many-to-many mapping, right? And we just look at a weighted combination of the cross entropies at individual times. You have a divergence, which you could minimize. And the weights could be chosen as you want. You might say that you might explicitly impose the constraint that I don't expect to be confident after seeing only one input, but as I see more and more, I expect to be more and more confident. So divergences down the line are more important than divergences early on. Or you could just say they're all equally important and just let things come out in the wash, right? Yes.
Will the longer
Correct. So longer ones you expect to actually would actually expect to see more evidence for,
Yeah.
for you know,
So will there be an average pulling like something?
we're not doing any average pulling. I've just given you a sequence. I've produced an output, right? So there's no averaging per se that's happening, right? I mean, you could be averaging the outputs. If you're averaging the output probability distributions, you're losing some information more than anything else.
So the longer it will have more powerful context.
In principle, right? You get more and more evidence. It's like having more and more data, right? So yes.
That's not necessarily true, right? Because if only after after three timestamps, that becomes these formula.
I'm not drawing any hard and fast rules over here, right? So that's why I introduced this notion of a weight, which tells you exactly how much, anything that you know about the nature of the structure, the nature of the problem.
So this will be weighted?
There's a weight I've actually written over here, right?
Oh, sorry.
Yes. So that would determine how you would actually choose to impose structure onto your problem, correct? The simplest thing is to just say all of them are one and let things come out in the wash.
What if I don't know the weight? Can you still apply that?
Yeah, I mean, there's nothing. I mean, our point being that the real problem is this, but this is losing information. So you're replacing it with this, and in most cases, this is going to be more useful, unless the output really is noise all the way to the end. But that's a very highly unlikely scenario in most cases, right?
Is this weight learnable or fixed?
I don't think it's learnable. I may be wrong, right? So,
Training MLP to evaluate your.
I mean, you could potentially do that. There are actually other there are approaches where you try to actually come up with ways of predicting the
Reinforce.
divergence function itself, but we won't go there, all right? So now here's a more complex problem, right? I've taken the same problem and I've changed the setting. Now, instead of giving you a segment and saying there's just only one output coming out, I give you a sequence of inputs, and I want you to asynchronously produce a sequence of outputs, right? I have this sequence of log spectral vectors. Tell me what phonemes happened when. Or I have this sequence of speech. Tell me what words happened when, right? So now this is asynchronous outputs, sequence of outputs in response to a synchronous, time synchronous sequence of inputs. And this is really just many concatenations of the simple problem that we just saw, right? But the simple extension makes things very difficult. Why so? Now, if I just gave you an input and say produce my outputs, right? What the network is really going to be doing is to give you a probability distribution over the symbols at each time. When do you know that you've changed over from one symbol to the next? You have no way of pinpointing the specific time instant where the symbol rolled over and you had to begin accumulating information for the next symbol.
Would you not know that by the probabilities dropping as you transition?
You're assuming, but you don't have that information a priori, right? So now we're going to have to make those inferences from the outputs that came out in the final layer. So, in fact, the network produces outputs at every time. We have to decide which of these is the real outputs. So what the network's really going to give you is that each time it's going to give you a probability distribution of all the symbols, right? And we are going to have to decide. Suppose all I did was to pick the most likely symbol at each time, right? Then I'm going to get one symbol per instant. But really, that's not what we want. What you're saying is that if the same symbol occurs sequentially many times, then you're saying, then you could say that, okay, this is all just a G. This is all just an F. This is all just an E. That's a D. The problem, of course, is that it doesn't let you distinguish between, two Fs and a single F, right? So, and the resulting sequence may be totally meaningless, right? What's feed? I have no idea, right? So now you want to really impose constraints on top of this. And you could impose constraints by saying, I only allow sequences that correspond to dictionary. Or we did something very interesting in homework 1. We're going to revisit this, right? Which was every phoneme had 3 parts, part 1, part 2, part 3, which meant that if part 1, you had many repetitions of part 1, you were guaranteed that it was just one instance of it. It was not 1 followed by 1, because we know that according to our structure, 1 must be followed by 2, right? 2 must be followed by 3. If I have a phoneme repeating, it's going to be the part 3 of the phoneme for being followed by part 1 of the phoneme. So the structure of the problem imposed extra constraints in homework 1, right? So you have ways of imposing structure on the problem which disambiguates between something like FF and a single F, right? So we sort of seen how we can actually come up with use this to make inferences. I have an input, I tell you something about the output. Let's go back and look at the other problem. I want to train. Now, if I were given output symbols at the right locations during training, all is fine. This is just the same problem that we always had. I can define a divergence at all of those locations. I can compute the gradients. I can propagate it backwards. I can even replicate these things, as we saw, right? And all else that we spoke still applies. The real issue is, suppose I told you these are the sequence of symbols that we saw, but I didn't tell you where. So now if I give you this, right, you have an issue. You have a sequence of outputs, but you don't know whether this guy must be compared to a B or an A. You don't know whether this guy is an A or a T. It might even be a B. You don't know exactly where the boundaries happened, right? So now you have this problem of figuring out the alignment of the symbols to the outputs before you compute your divergence. And each alignment is going to give you a different divergence. So if I align my symbols like so, and then I computed my divergence, I'm going to get some divergence. I could actually have, I'd still be adding divergences at individual times using this the simple approximation assumption that we made earlier, except that we don't know what this guy is. If I specified an alignment, you'd get a divergence, but if I specified a different alignment, you'd get a different divergence, and yet another alignment, I'd get yet another divergence. Depending on the alignment, I'm going to get different divergences, right? So the problem is that, what is the time here? 0, okay. Any of these alignments is possible. We have no idea a priori what the alignments might be. Given this, what can I possibly do? I'm given the high-level sequence of symbols, but I've not told you, I've not given you the low-level information about where the boundaries actually lay and how I must align this high-level sequence of symbols to the outputs to compute the divergence, right? So in this case, the obvious thing for me to do is to say, okay, let me consider all of them. I have no idea which one it is. I'm just going to consider the entire lot. And the way I'm going to consider the entire lot is I'm going to compute a weight for each alignment and multiply the divergence for that alignment with the weight for the alignment, and I would compute a weighted combination of the divergences for every possible alignment, right? So if I were to write it like so, this S1 through Sn, the reason I'm actually not completing this today is that the notation got to be tedious. I've got to figure out what is the simplest way of presenting this, but S1 through Sn is an alignment, which means it's actually a sequence of symbols, right? Phoneme, 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 or character, 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 whatever else it might be. But there are many possible sequences corresponding to a given high-level sequence, right? So if I have n possible outputs, the high-level sequence is going to have k symbols in it, which is where k is less than or equal to n, right? Can't be greater than n. So I have many ways of expanding these k symbols into n by repeating things. And so for each one of these possible expansions, I will have a weight, and I'm going to compute the divergence for that expansion. And this is the total divergence that I will that I will actually use, right? Now, when I begin writing things like so, what do you think is going to be a reasonable guess for what this weight must be? Anyone? You can think of plausibility, right? So, for example, you would almost certainly not expect to see the first 5 symbols all squished in the beginning and the 6th extended for 100 symbols, right? Or the reverse happening. Or if I'm expecting the word 0, right, and I'm looking at the phoneme E, it's not going to be just one phoneme long. The R is not going to be, nobody says 0, so the R is not going to be 10 phonemes, 10 frames long. You have all of these intrinsic notions of what is likely and what is not. So you want to give less weight to less likely alignments and more weight to more likely alignments. Let's quantify this. I can say I want to weigh by the probability of the alignment. So what is this thing that we're actually looking at over here? This is the expected divergence over all alignments, right? Every alignment has a probability. The probability itself is derived from the output of the network, right? And now I can compute an expected divergence over all alignments. And what I'm going to try to minimize is that instead of choosing any single alignment and computing the divergence with respect to this, I'm going to consider the expected divergence over all possible alignments. Make sense to you guys, right? Now, what would a simpler alternative to this be? Anyone? I could just choose the most likely alignment, right? And then just compute the error with respect to the most likely alignment and divergence with respect to the most likely alignment and minimize that. But when I minimize that, the most likely alignment will change. So I could actually have an iterated process where at each time I find the most likely alignment, find error, and repeat the process. So these are 2 alternate ways of doing this. Now, when you want to look at the expected alignment, divergence, we need to compute this posterior probability of a particular alignment given the input, because that's how we're going to be computing the expected divergence. And computing this guy turns out to be a bit tricky, not because the basic arithmetic itself is hard, but because of how you set up the problem. And so this is what we'll go into in the next class. Again, keep in mind that the problem that we are really addressing is that you're given a sequence of inputs and you're trying to produce an asynchronous sequence of outputs. Many instances of this problem, like speech recognition, where I have a sequence of speech coming in, I'm trying to produce phonemes, speech coming in, words coming out, machine translation, words coming in, words coming out, different kinds of things, right? But again, the problem is sequences coming in and sequences coming out, going out, and there's no synchrony. And in this case, how exactly do you compute a divergence that you can minimize, right? I'll stop over here. Questions, anyone? Yes?
What happens to a scenario when output length is not equal to the desired output length?
Meaning?
When the network generates an output which is of length less than...
So the way we set it, the network is, okay. The way we set it up, at least for training, the network is the output symbol sequence is less than or equal to the length of the input sequence, right? But you can always have a setting where the output sequence is longer than the length of the input sequence. It's not something that I've not actually addressed over here. We'll consider that in the next class, because then you go into a generative mode, right? What this means is that I've got to produce a sequence of inputs. At some point, the sequence ends, but the output can continue to generate, and we know how to do that already. This was the first problem that we addressed. So this is just a concatenation of 2 components now over here, where the second component was the first problem that we addressed. And then you have to combine the losses. Anyone? Yes?
Generally speaking, for the LSTM or the recurrent neural network, how do we initialize the hidden state?
So you're going to have a homework. You'll figure this out. But mostly, in all of the standard tricks for initializing these neural networks apply, right? Varies from being completely random to anything else.
Completely random or
Yeah.
if I randomly initialize the initial hidden state,
Mm-hmm.
should I need to save it as part of the model, or next time when I?
So no, again, remember that you're actually processing the entire input, and then you output, and then you're going to update your parameters. Your parameters are going to be updated every training instance or every batch of training instances, right?
So initial hidden state is also part of the parameter.
The H1 is also part of the parameters,
Okay.
right? That's part of the parameters. Right. H minus 1, right?
Yeah.
That's part of the parameters. Yeah. Thank you.